Okay, so we'll continue with moving shock. We have used the notations for a moving shock in the previous lecture. So the notations are for stationary coordinates. We have used 1 and 2, correct, and for moving coordinates it's x and y before and after the shock. So stationary coordinates means it's also your moving shock, okay, and if I travel along with the shock, that is a moving coordinates and that is a stationary shock. Okay. So to match with the stationary shock notation that we have used before, I have used x and y and this. Okay. So we have seen how the static quantities are same for your moving as well as coordinate, moving as well as stationary coordinates. We because they are measured, static quantities are measured while traveling along with the fluid. And hence the static quantities in stationary coordinates as well as your moving coordinates are the same. So now we will understand the problem better if we do a numerical problem. So I have a problem here which shock moves with velocity, let us take 500 meters per second into a still air. Fluid is gamma 1.4. So the still air has pressure is let us take it as 100 kilopascal and still air temperature is around 20 degrees Celsius. Find the static and stagnation quantities after the shock has passed the medium, or at some locations when the shock has moved, what is the property, the static property and stagnation properties in the flow. So I have a shock that is moving with velocity 500 meters per second. Okay, it is moving into a still air, and still air property is given. P is 1000 kilopascal and temperature is 293 Kelvin. So as it passes, it changes the properties here. So what is the property after the shock has passed? Okay, so we will do the problem the way we know. So I have stationary coordinates here. I have a moving coordinates here. As I told you, stationary coordinates also means the observer is stationary, which means it's a moving shock. This is a stationary shock. So I have a shock here. This is 1 and 2. I have a shock here with x and y. Okay. So the shock is moving this way. So the shock is moving this way. Maybe I will write it the way we had written. It was 1 and 2 the other way, right? So we will say this as 2 and 1. So the shock is moving with some velocity, and this is y and x. Both should be same, but so there is a yeah, this is x and y. Okay. So we will do from the information we know. First is the velocity of the shock is 500 meters per second, which is our Vs. So in the stationary shock, I will be facing the fluid which is moving at a velocity Vs, and I would see the fluid receding me with Vs minus V. Okay. So the velocity here is V. Okay. Now we know the pressure and temperature in the stagnant fluid, which means this is my P1 is 100 kilopascal, T1 is 293 Kelvin. We know that this static pressure and temperature would be same as in the coordinates whether it is moving or stationary. So this is also our Px and Tx. So Px is 100 kilopascal, Tx is 293 Kelvin. So this stationary coordinates or moving coordinates or stationary wave, stationary shock wave, we have the static quantities the same as what is written here. But we also know that this is for velocity 0. So this is also my P01 because the velocity is 0, and my T01 is 293 Kelvin. Vs we know as 500 meters per second. So my Mx is Vs by Ax, which is 500 by gamma r Tx, which is and 1.46. Okay. So this is a stationary shock wave. So now I know my Mx, from which I can find my My from shock tables. because now the wave is shock wave is stationary, I can use the shock wave tables. I would get my to be for gamma equals 1.4. I will use shock tables to get 1.46. My my is 0.716. 0.716. So now I know my my. I will also get Ty by Tx. Again from shock tables. So Ty by Tx is for 1.46. Ty by Tx is 1.294, hence my Ty is, and likewise my Py by Px is 2.320, and hence my Py is 379.14 Kelvin, and Py is 2 kilopascal. Okay. So now I know these values. From which my my is Vs minus V divided by Ay. Now since I know my Ty, I can find my Ay. So my is 0.716 equals Vs minus V divided by gamma R Ty. So Vs also we know as 500. From which I can find my V. Yeah. 220.5 meters per second. Okay. So my V is now 224. So I see a fluid shock that is coming, and the relative velocity after that is 220. V is 220.6. So the velocity here, the relative velocity is 500 minus 220 is 279.5. Okay. So the fluid is receding with a velocity 279.5 meters per second. If the fluid is coming and hitting with the shock wave, standing shock wave with this. I can also find my P0x from this, since I know my mx. So all these are from shock tables. Now I can use isentropic tables to find my P0 Px by P0x for mx. So I use the isentropic tables. Mx is 1.46. Mx is 1.46. This ratio is 0.288 from isentropic tables. So my P0x is 347.2 kilopascal. Likewise, I can find my T0x to be from the ratio Tx by T0x is 0.70 multiplied by this is T0, yeah, is again from isentropic tables, which is okay. So these are the quantities in the stationary wave or moving coordinates. If I move along with the shock wave, these are the changes I would feel. Okay. Now we have to find what is happening in the moving wave. So the static quantities are going to be the same. Since I know my Ty and Py, I can write this as P2 the same as my Py, which I can copy it from that, which is 232 kilopascal. Okay. And T2 the same as my Ty is equal to 379.14 Kelvin. My V is calculated to be 0.5 meters per second. Okay. So these things we have obtained from the other value, from which I can find my M1 is 0 because my V is stagnant fluid here. So my V1 is 0. So V1 by A1 is 0, but my M2 is V by A2. V is 22.5 meters per second divided by gamma R. T2 is Ty is 375. This is 0.56. Okay. So a stagnant fluid is there, a shock comes and moves, it gains this much velocity, 0.56. So if I know my Mach number, I can find all these stagnation quantities, P0, P1 by P01 for M2. I look at the isentropic tables, 0.52, sorry, P2 by P02 for 0.56 was 0.808. Okay, which gives me a P02 of 287.13 kilopascal. Likewise, I can get my T02 T02 is 0.941 divided by 0.941, again from isentropic tables, this ratio, this is 402.9, okay, Kelvin. So now we have the answer. I have a stagnant fluid, the shock is coming and moving into this pressure and temperature. Okay. So this pressure and temperature, if the shock is moving with a velocity 500 meters per second, I am going to increase my stagnation pressure into this much, stagnation temperature by this much, and my fluid, which is 0 velocity here, gains a velocity of 220 meters per second, by which the Mach number is also different. Mach number has changed from 0 to 0.56. Okay. So, the shock wave brings this much change in your fluid. Okay. So, we have obtained this by transforming the coordinates, doing computing the properties across the shock from the moving coordinates, where we assume this shock to be stationary, and obtained all the properties, and then map it to this particular coordinate system, where we know the static quantities are not going to change irrespective of the coordinate transformation. Okay. So, with this I think you can do any kind of problem, even when the fluid here, even if the V here is not stationary, except that you cannot equate P01 equals P1. Okay. So, if the fluid velocity, if you have a finite velocity here, then P1 and P01 cannot be equated, and T1 and T01 cannot be equated, otherwise everything is same. Okay. Okay, so that brings a small discussion into the small discussion on moving shock. Now we will proceed to oblique shock waves.